everyone, and welcome to this webinar on Introduction to Signal Processing. Now, before we begin, let me walk you through the contents of this webinar. So we'll first start with a basic introduction to this topic. We'll understand what signals mean, what signal processing is, and then get a general idea about the vast applications of signal processing with some examples. Then we'll have a detailed discussions here where we'll go into the important fundamentals. But please note that in interest of time, I'll be limiting myself to only a few important and practical concepts and not delve too much into the mathematics as of now. So after the basic fundamentals, we will have a look at a simple case study of signal processing. This is like a real world example of signal processing in order to understand how it is used in real world. Then we will go through the evolution of the field, where we'll see the state of the art, which means the current trends, and also see what the future holds for us in this field. Then towards the end, we will uncover some of the practical skills that you need to enter and excel in this field. And we'll see how to land a job in this particular field, along with the prospects in the Indian market. Okay, so let's begin. So in order to understand signal processing, first, let's have a look at the meaning of signals. So the textbook definition of signal is that it's a measurable piece of information that reflects a real world phenomenon. Now, I'll give a few examples here for explaining better. So you know audio signal, right, which is sound, and video signal, which is a sequence of images, and it could be motion, which means acceleration or velocity, or it could be voltage, current, etc. So all these signals that you have in real world, these can be measured with sensors. So sensors are common in all signal processing systems, and sensors are these devices which convert real world signals into a form which a computer can understand. Now, some of the examples of sensors are a microphone, which captures audio. Then there is CMOS camera, which captures videos. And then there is inertial measurement unit, or IMU, which captures motion. So now that you know what signals are, signal processing is this little box over here, which accepts signals at its input, and it does some kind of meaningful calculation and processing on these signals, and it outputs a cleaned up signal or a decision or something similar to that. And this processing that you see here is generally done by some electronic circuit, an electronic board, which typically has a microcontroller or a processor on this. Now, before we move further, keep in mind that in today's session, we are mainly addressing systems which do signal processing in real time. And that is because we are generally not interested in first capturing, then storing, and then processing it in a general purpose PC. Because the main use of signal processing in industry is to do it on the fly or in real time to accomplish something. Now, for example, when you tilt your mobile screen while in auto rotate mode, the IMU sensor in your phone quickly calculates the orientation of the phone, and processor could then decide to rotate the screen from landscape mode to portrait mode, for example. Now, all this is useful only if you are doing the processing in real time, right? And won't make much sense if the screen rotates after 20 seconds or so. So the main use cases of signal processing in industry is mostly in the real-time domain. Now, looking at some of the applications, signal processing is one of the field which has the most wide field of applications, and I don't say this lightly. There is healthcare sector, there is automotive sector, there is aerospace and defense, robotics, industrial applications, and so many other fields which directly use signal processing. In the next few slides, we'll look at some of the applications in each of these fields, and we'll also have some examples on the way. So first one is biomedical or healthcare sector. Now, all of you must have seen these kind of ECG graphs, right? Now, ECGs are the small electrical signals that your heart emits as it beats. From these signals, you can potentially understand the health of your heart. Okay. In fact, there are some startup companies these days which have designed wearable products like a wristwatch kind of device, which captures ECG signals and does signal processing on it. And these devices can then alert you about the risk of a stroke or an attack, or tell you whether your heart is beating in a proper rhythm or not. Now, I'm sure you must have heard about ECG signals before, but did you also know that our brain emits something called as EEG waves or electroencephalogram waves? And if you try to tap the voltages appearing on the scalp of your head at different locations, and that can be done with a few electrodes. So by doing that, you can actually make out what your brain is thinking. Isn't it interesting? Now, these electrodes are mounted in a cap-like frame that can measure small signals that appear on your scalp, something in the range of 50 to 60 microvolts, which is a very small signal. In fact, I got an opportunity in past to briefly work in a project on EEG waves in an Indian research labs, where we were working on a proof of concept of a wheelchair that is controlled only by what the user is thinking. So the wheelchair could turn left or right or stop based on just the thoughts of the user. And that was completely done with the help of these EEG signals. So isn't it quite fascinating? Now, these EEG signals don't look as intuitive as ECG signals, right? And these signals require a lot of mathematical calculations and transformation with signal processing in order to make out what the brain might be thinking. There are something called as alpha waves, beta waves, which reflect different kinds of thoughts. So this is another application of signal processing in this field. And there are many others too, like MRI and X-ray imaging in healthcare field, so which are based on image processing. Coming to the next field, which is automotive. So these days there are companies, I'm sure you must have heard of Tesla and Waymo and many other companies which are working on self-driving cars, right? So these are also called as autonomous driver assistance systems or ADAS systems. So here various sensors like radars, lidars, and many cameras are mounted on a car, around the car, and their data is processed and fused to give information of the surrounding of the car. These make the autopilot in the car, the self-driving car, to take correct decisions, to turn the car or drive it. So another application of signal processing here. It's basically called as data or sensor fusion, where you have multiple sensors and the data is collected from all of them and it drives the autopilot. Another one is engine control. So a typical car these days have got tens of different sensors in its engine itself. Like there is oxygen flow sensor, air inflow sensor, temperature sensors, and so on. These sensors are used to regulate the combustion of engine by controlling various flow valves inside the engine itself. Now, all these different signals like fuel sensors and temperature sensors require signal processing, right? And is generally done with a microcontroller called as ECU that sits inside the car. Next one, I guess you might have heard about this. You must have seen some commercials of vehicles on TV where a person is speaking to his car for simple tasks, like tasks like turning on the music or commanding the temperature of air conditioning or switching on the navigation. Now, this is an example of speech processing or speech recognition, and quite widely used again. And apart from these three applications that you see here, there is also infotainment applications in modern car, which uses video processing and compression and overlay for displaying various information about the car and also for entertainment. And the next interesting field is aerospace and defense. Now, you might have heard about or read about the fifth generation fighter aircrafts like Rafale, which have got this ASA radar. So ASA radar is the shorthand for active electronically scanned array radars. And this is the one that you see on the nose of the aircraft in the image. It is mounted right at the front of the aircraft. So this sensor array that you see, these are like the replacement for traditionally heavy rotating radars that were quite common. And these are much smaller and lightweight radars, and it's stationary also. So these array of radars also have a lot of signal processing going on in order to locate other aircraft and that is done by basically checking the signal echo in the sky, and while rejecting any unwanted noise, like those coming from small birds or some other sources. So these ESA radars have enabled radars to be mounted directly on smaller aircrafts that you see these days. And before these rotating radars that were traditionally used, they were placed on larger aircrafts, which needed to accompany, fighter jets in a real mission, which is quite inefficient, obviously. Or in other cases, the big rotating radars were mounted on ground in a fixed location. So that obviously limited the abilities for range of these aircrafts for detection. So another example, next one that you see is the anti-aircraft missiles. So anti-aircraft missiles have got something called as a seeker head on the nose of its body. It's right in front of it. And these seeker heads contain a thermal imager camera. So it's a night vision kind of camera. And these cameras detect the heat signature of the target. So what you see here in the image, that is what the nose mounted thermal camera sees. Okay, so here you can see there is this exhaust coming out of the aircraft. Then this aircraft has got a typical shape. So based on these details, there are video processing algorithms that run on the missile seeker heads, and this basically guides the or helps the guidance and control systems of that particular missile to home in on that target. So the task of that missile seeker head or the control system here is to keep the target at the center of the image, so that the missile is heading directly for the aircraft. So again, very interesting application of signal processing, specifically speaking, image processing here. And apart from that, again, signal processing is used in a lot of other kinds of signal processing in aerospace and defense sector. Apart from these, there are various other fields of application of signal processing, like Industry 4.0, which is the modern technologically capable industry. And some of the examples here are predictive maintenance, which means you see this motor in the image. So something like this are used to drive a conveyor belt or some kind of machinery in industry. And on top of this, you can actually attach a sensor, motion detection or a vibration sensor on the body of this. So it's completely non-intrusive. And these sensors mounted on the body can measure the vibration or sound that the motors make. And based on signal processing done on these sound signals, there are algorithms now which can predict when the machine is about to fail, right? So this has got a lot of economic advantages by basically reducing the downtimes caused by unexpected failures of the machine. So it helps in maintaining the machinery effectively and more efficiently. Then there is also IIoT, which is Industrial Internet of Things. So again, here you've got a lot of sensors distributed on the industry premises, and these collect signals from various locations. And wherever there are sensors and signals, there will be local signal processing, before forwarding it to a main server. So signal processing finds its way into these devices also. And another application is robotics also, where motion control is one of the major challenges in robotics. So all moving robots need a smooth motion within given constraints. So here a lot of motion sensors like gyroscope, accelerometer, magnetometer, rotatory encoders, and etc. are used, for detecting the motion, and signal processing is done on these. So similarly, there is the SLAM technique, which is the localization of a robot in an environment, for example, without a GPS. So again, this uses sensor fusion or signal processing as one of these steps. Okay, and apart from these, in robotics itself, there are a lot of applications of machine vision, where you have camera mounted on the robot looking at its surrounding, and the robot can then do complex tasks like picking up objects, performing surgeries, and so on. So all that is accomplished with very sophisticated video processing or computer vision. So now let us try to dig deeper into some of the basic concepts of signal processing. So signal processing primarily consists of three main stages. Okay, first is the signal acquisition, then signal conditioning, and finally the output or decision making, which can be another signal or a decision. So in the first step, we have got acquisition of signal. Now here there are some sensors attached to your signal processing systems, which can give analog readings, right? Analog waves, and an analog to digital converter, which is called as ADC, does this acquisition of analog signals and converts into digital format, which a computer can understand. And in some other cases, if the sensor is giving out the signal on a digital interface, then there are some device drivers used here. So serial communication interfaces like UART, serial SPI, and I2C, these messages are parsed in the firmware and fed to the microcontroller or a specialized digital signal processor with the signal, which does the signal processing. And the second step that you see, signal conditioning. Now this is where all the magic happens. It is generally implemented in software using some sophisticated algorithms, and it is done on some microcontrollers, or it could be an FPGA or a processor, or even some specialized ASICs or ICs. So this step usually consists of some kind of filtering or compression and prediction that happens. And most of the signal processing today happens in software, like I said, but some processing could also happen in hardware too. For example, in the first step itself, signal acquisition step, there are some RC filters, resistor and capacitor based filters, to prevent any noise or any interference from other signals to corrupt your base signal. And finally, there is this decision making step, which is like the output of the system. Now, this output could be driving an actuator like a motor or a valve or something like that. And that uses a DAC, which is digital to analog converter. It's just the opposite of ADC. And it could also be a PWM signal. These signals can drive different kinds of actuators, which are controlling your either your car or your airplane or a missile, whatever it could be. Or in some cases also, there are this HMI interface, which is human to machine interface. So which is like a display. So if you want to display a graph or something on a screen, like in the case of medical imaging, this is the output of the signal processing system. And in some other cases, it could be like a message being sent over the internet, right, to alert you about something. So these are some of the basic stages in signal processing. Now coming to some of the concepts used here, filtering is one of the most important concepts in signal processing. Okay, this filtering basically removes any noise or any unwanted signal from your system. Okay, so here you can see in this example, we have a graph of a typical current versus time signal. So the one that you see in blue is the raw capture data from, let's say, an ADC. So obviously you can see there are a lot of spikes here, which is quite common in a real world sensor capturing a signal. But with so much noise, it could probably not be very useful. So you need to apply some kind of low pass filtering here in order to remove this noise. And the waveform that you see here in green is the filtered waveform. So you can see, because of filtering, the waveform has smoothened out quite a lot, and this could probably be driving another motor or some kind of output, which is useful. So this is one of the applications of filtering. And there are lots of kinds of filter. Like there is low pass filter, which basically lets the low frequency components pass and blocks any high frequency noise, like you see here. This is high frequency spikes. Okay, then there could be high pass filters in some other examples where, for example, you want to block any offset or a DC signal, a constant signal, and you only want to let some kind of sinusoidal signal into your system. So this is where high pass filters will come into picture. And band pass is something between low pass and high pass. It's only like a band of frequency that are allowed to pass through the filter. There are a lot of software algorithms these days which are used for achieving this kind of filtering. The next one is transformation, and specifically time domain to frequency domain transformation. Again, very important concept used in signal processing. Suppose, like in the previous case, you saw that the current graph was plotted as x-axis with time, right? But in some cases, you're probably not interested much about how the signal varies with time, but rather you want to know what are the details in the frequency domain, which means you want to know what different frequencies of sinusoids your signal is made up of, like you see here. Now, for example, you're designing a device, an electronic device, okay, and it works perfectly fine outdoors. But when you get it indoors in your house, you see some kind of random noise appearing, okay, and then suppose you do a frequency transformation from time domain to frequency domain, you see that there is a small spike like this appearing at say 50 hertz, and only while operating inside the house. Now, based on this information, for example, you could interpret that this is happening because of some kind of interference from your main power signals, like the AC frequency at your house is 50 hertz, right? So you can interpret those results based on frequency domain, and something which would not have been possible by just looking at this random signal in time domain. So by knowing this, then you could probably prevent from those AC power lines from interfering with your device, or you could apply some kind of filtering in hardware or software inside your device. So it's quite useful here. And apart from this particular kind of transformation is also useful for visualization of your signal, to know what are the different kinds of signals your main signal is composed of. Okay, so that is another use case. Another important concept is signal compression. Now, let me give you a very simple example for this. So nowadays you see HD videos, which are videos of the resolution of 1920 cross 1080 pixels, right? This resolution, and you see those videos in your phone while streaming from say YouTube or a live cricket match, right? So it has some 30 frames per second. It is repeating, or it is updating every 30 times in a second. So if you do some quick math on it, you'll realize that the total bandwidth, by multiplying all these numbers and finding the bits per second, right, you'll get a video bandwidth that touches almost 1 gigabits per second. And that's a very high number for bandwidth. And you also know that your typical internet speed is around say 10 to 100 Mbps max, right? So then how is the streaming possible? You have on one side 1 gigabit per second speed of video, and you have internet connection which is a few tens of Mbps probably. So the answer for this is video compression in this case. So what it does is it identifies different redundancy in your video. So for example, from one frame to the other, there are algorithms which can recognize that only a small part of the video has changed between the two different frames, and it will encode this kind of information using these algorithms and accomplish a much lesser bandwidth at the output. So this is quite commonly used in different video and audio processing applications where you want to communicate or store this kind of messages on the internet, say, and so on. And in this cases, on the receiving end, whenever you send this on the receiving end, for example, in your mobile phones, there is the opposite that happens, decompression or decoding of the signal, which again gets it back to the 1 gigabit per second signal in your mobile device. So as you've seen, it's got a wide range of application, signal compression. So these are some of the basic fundamentals that you have seen.